I thought before we actually get to this derivation and how we do each of that, I'll just give you a brief review of why do we want squiggle at all? Why are we going after squiggle? Why do we want these functions? Because at the end of the day, this function is going to be a function of things like temperature, pressure, moles of species that we have, and that's usually what we want coming out of a reactor. And we typically relate those moles of species through the extent of reaction. And so if we can arrange this form somehow that we can solve for an extent of reaction, it works like another piece of information about a reactor. So for example, in 100, we would frequently see an example of something like this. Just a single inlet and a single outlet to a reactor. And we would want to know, for example, the conversion of some species inside there. We had called conversion F in most of those classes. If some kind of reaction were occurring in here, like A plus B goes to C plus D, we often had a little bit of information about what was coming in. So there might be 1 mole of A and 2 moles of B coming in. And then there's some unknown amount of A, B, C, and D coming out. Often we would then ask you in a homework problem somewhere, figure out what the conversion of A is. And we would have to give you some additional piece of information like the moles of B coming out was something else, or the moles of D coming out was something else. Or maybe we would tell you the conversion and ask you to calculate the moles. Either way, it could do either direction. Usually the way that we would go about solving something like this is a stoichiometric table, which can be set up in a number of different ways. The way that you'll often see me setting it up looks something like this. So we have at least 4 columns. Usually there's or sometimes there's a 5th column, a delta. Some people put a delta column right here. That's okay, you can add the delta column if you want. And the moles coming out, we would always figure out based on the moles coming in, and that product of the stoichiometric coefficient times the extent of reaction. That hasn't changed, right? That still holds. That was CENG 100, works for 113 too. And so we would fill this out with each one of these species. Remember, the stoichiometric coefficients are negative for reactants and positive for products. Fill in how much of everything is coming in. So we had 1A, 2B, no C, and no D. And then we would use that expression for the moles coming out as a function of the stoichiometric, or sorry, a function of the extent of reaction squiggle to say things like, okay, the moles of A has to be equal to 1 minus squiggle, moles of B is 2 minus 2, wait, 2 minus 1. I can't actually see that stoichiometry on my page. Moles of C, initially there's nothing, so we just make some at a rate of squiggle. Moles of D, we make some at a rate of squiggle. If we needed to, we could sum all these things up, right? Initially there was 3, coming out afterwards there's still 3. That should look like the general approach that we used in 100. What we're doing with that equation that I had on the previous part, what we're doing in general when we say equilibrium is achieved when the Gibbs energy is minimized, is trying to give us another piece of information that goes on here. So that piece of information, it will never look quite this simple, but we will actually, you will derive essentially this kind of equation on one of your homeworks. We just never have the need to actually write it out like this. It's an equation like any other equation. It's got a bunch of constants, and it's a function of squiggle. Where are these numbers coming from? I made them up specifically for this example. That's essentially what we're doing, though, with the discussion we have yesterday, today, and tomorrow, and Friday, is figuring out how do we get a form for that. Usually we don't actually use that particular form, right? We take the partial derivative of that with respect to squiggle, which isn't too bad in this case, it's a polynomial, and we figure out what's the value of squiggle that makes that partial differential 0. So if I were to try to do something like that, actually I think I'll just show you what the plot looks like. If I were to plot g of t here as a function of squiggle, sorry, not g of t, g superscript t, you get something like this. So the lower end would be about 550. The upper end, what did I write? About 1,000. And there's a minimum right about here. That minimum corresponds to a specific value of the extent of reaction, which if you go through and work all that math out, corresponds to about 0.48. And so this is another way of us giving you that information. I don't have to give, or I will not have to give you G by the time we're done with all of this discussion. All I will have to tell you is the reactor goes to equilibrium, right? If it goes to equilibrium, then you can use all the tools that we're developing this week, essentially to figure out what that value of squiggle is. Once you know what that value of squiggle is, I can come back over here to my stoichiometric table, plug in all those numbers, and I can figure out how many moles of everything are coming out. So it's another way that we provide a condition for a reactor. We're going to use it in a different way next week, but even next week, it's still another condition we can use to help us learn something about our reactor. If you don't recall the definition of conversion, it was in minus out over in. So if we want the conversion of A, it was all of that for species A. And that definition doesn't change. We're going to change the symbols that we're using for that later, next week, simply because everybody by convention uses a different symbol in reaction engineering, but the concept doesn't change. So if we had to solve this like it was a 100 problem and the original question was, tell me what the conversion of A is, we could use that expression for the Gibbs energy to find out what squiggle is at equilibrium, put that back into our stoichiometric table, and then, put those results into the conversion. That's generally the process that we're doing here. Yeah? How did I get the boxed function here? How did I find G as a function of what? Squiggle? We're about to show how that works out. So this one I just arbitrarily made up some kind of a function to describe what that process would look like. It'll never look that clean because there's an enormous number of terms that go into there. But essentially that's what we're doing is we have G on one side and nothing but squiggle on the other side. If we crank the wheels of math enough, we can back out something like that. Or we can just flat out plot it. And that's what you're doing on the last homework problem. Is there's not really a clean way to do that in a closed form, but if you dump it through MATLAB, you can develop exactly that plot. And that can help you find that minimum in there. But anyway, finding that particular form is what we're about to do. So that said, actually, any other questions? That was a good question. This is generally what you do when you're done, right? Once you figure out what squiggle is, you use it somewhere in a stoichiometric table. Okay, let's get part of squiggle. It takes us 2 days to get squiggle, but we will get there. Anybody remember what the, what were those? The fundamental properties of G. It was based on two parameters, temperature and pressure. So somewhere in 103, 102, you would have seen that G is a function of T and P. I don't know if you would have gotten to the point where you were talking about multiple species. That is what we would write. If we just had to say a single species, we could close this parentheses here and say the Gibbs free energy for a free species is a function of nothing except temperature and pressure. If we have multiple species or those species are interacting, it's still a function of temperature and pressure, but now it's also a function of the moles of each component. If we were to write this as a total derivative, right? If we wanted to know the change of the Gibbs free energy G as a function of all of those, we don't actually need any thermo to do that. We can write all of that just knowing what the definition of a total derivative is. So the total derivative dg is kind of a cop, well, it's not really a cop-out. It's okay. It works. It doesn't say a lot, right? So we can say it's the partial derivative of G with respect to T, holding P and N sub I constant, times the change in temperature. That's nothing except the definition of the total derivative. We have to add another term to complete our definition, and we just go through each of these one at a time. So we would take the partial derivative of g with respect to t, but holding t and n constant, and multiply by the change in pressure, plus the last one usually looks kind of nasty because it's a big sum. Partial g partial n sub I, holding temperature and pressure and all the other n's, right? We have to do one at a time. All the n sub i's that are not equal to this particular one times that change. So if there's multiple species, we have to sum up every one of those. If there's 10 species, there's 10 terms inside that sum, and it goes all the way out. That's the shorthand way of writing. Ooh, that's a really bad sigma right there. This is permanent, so I like to get those symbols correct. And that's generally what we would do. We haven't done any thermo right there, right? All we've done is math. We've said on the first line, Gibbs free energy is defined that way as a function of Tp and n. And on the second line, we said, well, according to the definition of a total derivative, that's what we've got afterwards. And since we're talking about the system, these are all superscript T. The thing that we were after, though, was partial GT, partial squiggle at constant temperature and pressure. So the constant temperature and pressure helps us in two ways. First, the constant temperature means I really do not care what this term is, because whatever that term is, it doesn't matter if it's positive, negative, complex, or not complex, it's always going to be multiplied by something that's zero. Right? If I'm holding temperature constant, it's going to be multiplied by dt, and dt will be 0, so we can get rid of that term. Same thing with the next term. I don't care how complicated the expression is for partial g, partial p, because it's always multiplied by the change in pressure, dp, and that's always going to be 0. So at the end of the day, we're really only left with that one on the end. The one on the end can be simplified in a couple of different ways, and we're going to use them all. This particular thing, for no reason other than we hate carrying that term around because there's, I don't know how many dozen different symbols right there, we have seen that previously defined as the chemical potential mu sub I. Right? Mu sub I was just defined that way. We don't like carrying that term around. You could do any of these derivations carrying that term around, and all you'll do is waste pencil lead or ink or whatever. So we had defined that as mu sub I. We also have one thing that helps us a little bit for this d sub ni. That is equal to the stoichiometric coefficient times d squiggle. Where do we get that from? Just take the partial derivative of our definition of squiggle, and you'll come up with that exact answer. Not too much that's on there. So if we now take that partial derivative down there and use this information that we've got up here, it simplifies quite a bit. And so we're down now to just the sum of the chemical potential times the stoichiometric coefficient times, oh, not Tn, d squiggle. A little bit better, right? We took that entire line on the middle from a total derivative, and now we've got it something that's a little bit simpler. We can rearrange it for the following reasons. Well, we actually don't have to rearrange it. We can apply that condition of equilibrium, which is that this has to be equal to 0 at equilibrium. Why is it equal to 0? Because yesterday we showed that that partial derivative has to be equal to 0. Now we've got something to work with, right? We have an equation. Presumably we're going to figure out how to take that chemical potential mu, this guy, and figure out how to express that as a function of squiggle, or do something similar so that we can solve something in there. But now we've got something to work with, which is this equation. It only holds at equilibrium, so don't forget that it's always only held at equilibrium. Mu sub I is one of those, we're going to work on the mu sub I for a little while because the mu sub I is not great. Chemical potential is nice mathematically. It's a nice conceptual idea, right? It's a little bit easier to write chemical potential as mu sub I rather than that nasty looking partial derivative every time I want to write it. It's not particularly helpful when it comes time to actually measure something in a lab somewhere or in a industry somewhere that you're actually wanting to know what's coming out of your reactor. Usually the more common form that we use instead of chemical potential is to take that mu sub I and turn it into a fugacity. And I can hear you checking out already, right? I can hear you saying, like, he's just making this stuff up. He's just like throwing up random letters and hoping that they eventually, you know, work out. Okay, A is a little harsh. B, I didn't make this stuff up, right? I didn't come up with all of thermodynamics yesterday. And C, I promise you it really will get easier once we work our way through all of that. We'll just have a couple of different cases where that fugacity becomes something useful. We are going to get there. It's just going to take us a little bit of time. This will also illustrate to you why the fugacity is a little bit more useful than something like a chemical potential, because we actually have closed forms for fugacity. Chemical potential, again, it's useful as like a thought tool when you're trying to figure out what these terms are doing. But when it comes time to actually apply them, we almost always drop back to that fugacity. The reason for that is the following definition. Right? I'm just throwing definitions out there at you. The change in the fugacity of a species, this is one of those great times where I don't have to try to derive this because we just flat out, oops, sorry, that was mu. We just flat out define it this way. Change in chemical potential is defined as RT times the change in the natural log of fugacity. Hooray. We went from mu sub I to RT and a natural log and another F. Not good. It does get better if we integrate these things over any given change, right? All I have to, if I want to know the difference in chemical potential between a pure component in one state and a pure component in any other state, doesn't matter what those two states are, any phase, any mixture, any temperature, any pressure. If I do that integral, all I'm going to do is go from a reference state initially and we have a particular name for those reference states that we'll get to in a minute. And we're going to integrate up over to F sub I with a hat on it and the actual mu sub I. Mathematicians hate it when we use the same variable on one of the integral limits as is the actual independent variable in there. You will sometimes see this with a prime on it. I don't think I really care to do that. You probably get an idea of what I'm doing there. At any rate, we're doing that particular integral. These two values down here at the bottom have a special symbol on them. They have this little guy here, the circle. It's not a zero, not that you can tell that it's a zero or a circle or an O. It is supposed to be a circle and not an O or a zero. Anytime you see any property M stands in for any property, this is defined as that property at a standard state. Standard states can change. Standard states are arbitrary. Well, they're not entirely arbitrary. You have to pay attention to what somebody else picked as the standard state, or if you choose the standard state, you need to let somebody else know what that is. The ones that we're going to do, the pure species, the standard states we're interested in are as follows. Therefore, a pure species. Anybody in here in bioengineering? I don't think we have bioengineers. Bioengineers don't use pure species as their standard states because you're never going to come across like a ball the size of that board over there of DNA, right? DNA just doesn't occur in those quantities. And so their standard states are usually not pure species. They're species in solution. Our standard state in almost all of chemical engineering is a pure species. But if you ever wander outside of like classical chemical engineering, their standard state may shift. It's always at a pressure of 1 bar, and we have a special symbol for that, which is P with a circle on it. Be really careful about that one. Even within chemical engineering, there are two standard pressures that are often used. One is 1 bar and one is 1 atm. They're almost identical, right? If you look at the conversion factor between 1 bar and 1 atm, they're really, really close. But if you're doing a fairly precise calculation, the difference there can throw you off quite a bit. So keep in mind, we're going to have to look up some tabulated values towards the end of the day. those tabulated values have to be tabulated in such a way that their standard state is the same as ours. All of ours will be tabulated at 1 bar, so it's not a problem. The other things are that it is phase dependent. So you have to look up, or you have to at least define, am I talking about a liquid, a gas, a solid, etc.? We primarily just use liquid, gas, solid. Again, if you go to like biology or something, they have aqueous as another one because it's in solution. And it can be at any temperature. So you just have to pick the temperature of the standard state. Oddly enough, those can conflict. You can pick a temperature that's not consistent with the phase, right? I could pick a standard state of liquid water at 450 Celsius, right? It doesn't, that thing will never exist, but I can still use it if I want to. Nobody does it because that's not particularly helpful. Okay, so if I do that integral now, so I've described to you what those circles mean. They mean we are working at the standard state. The top part of the integral, I need to know what these are. These are the species in mixtures. So the integral that I'm doing there is trying to change the environment in which these things are existing. On the bottom, they're going from a standard state and pure, and up on the top, they're going to a mixture of a lot of different things. And so that's sort of an abstract looking integral there because we don't actually substitute in numbers. We're more talking about concepts instead of numbers. But if we do something like that, we get a little bit of help. I'm going to have to move over here on the slide. Because what we end up finding is that mu sub I will be equal to G sub I circle plus RT natural log of the Fi hat. Remember, the hat just means we are now in solution instead of a pure species, over Fi circle. Remember, the circle means that was the pure species all by itself at some standard state. The reason that that's helpful is we then stick that into the previous expression that we had, which was 0 was equal to the sum of the stoichiometric coefficients mu sub I times, nu sub I times mu sub I. Oh, I think I actually skipped it. No, that was okay. Isn't that what I wrote on the last one? Yeah. This part. Sorry, I carried one too many derivatives around. Erase that D squiggle that was there. The D squiggle was moved to the left. If you look at the middle equation, the dgt was on the left and the D squiggle was essentially on the right. When I moved down one, I moved that D squiggle over onto the left and I forgot to erase it from the right. Anyway, we're left with this, and now I can substitute in that previous expression. So instead of, did I go too fast right there? Do you need me to go back? Usually when I hear mumbling when I change screens, I assume that that means I went too fast. You can always yell out and say, you went too fast, you're a moron, please go back. Again, a little harsh. It's not necessary to name call. Fi hat over Fi circle. Haven't done anything there beyond algebra, which is to substitute that mu sub I into the previous expression that we had. We're going to do one particular operation a lot in the sense that you're going to see it about 4 different times. You'll see there's a pattern that shows up a lot, which is a stoichiometric coefficient, nu sub I, times some kind of a property, and then summed. The sum there means sum it over all the things that are in your system, right? If there's 50 different components, then that value of I takes 50 different values of species A, species B, species D, species E, all of those things. So in general, whenever we see that sort of an expression, whenever we see a sum of a stoichiometric coefficient times any pure species component I, what that is saying is stoichiometric coefficient of A times that property of A plus stoichiometric coefficient of B times that property for B, all the way up to as many of those as you have, right? The last one, stoichiometric coefficient of I times that property of I. That's what that sum means. If you were to write all of that out, that's what it would look like. We have a shorthand for that because we don't like carrying the sum around all the time. We simply define any one of those changes as a delta. Notice the delta loses the subscript I, right? The subscript I went away because we summed all these things up. At the end of the day, it's just a number. So if M was like the molar mass of whatever your solution happened to be, you would calculate some kind of a weird-looking delta molar mass over here, and that would be that. So when I have this expression as the stoichiometric coefficient mu sub I times G sub I circle, I can replace that with a delta G circle, and that's what I'm going to do. Let me change that color just so you can see this. This particular term here is going to get replaced with a delta G circle. And then what I'm going to do is rearrange that a little bit. I'm going to have the delta G circle on one side, and I'm going to have this RT ln of F on the other side, so that instead of having something equal to 0, I'll have something on the left is equal to something on the right. If I rearrange both of those, I get this. And I'm giving this a fair amount of space here because we're going to talk about things in a minute. Pi, anybody seen the pi operator before? It's like a sum except for a product. It just means you multiply everything together instead of summing everything together. Fi to the hat, Fi hat, not Fi to the hat, over Fi circle, raised to the stoichiometric coefficient I, nu I, is now equal to the exponential of minus delta G circle divided by RT. That's a pretty big expression that we're going to spend most of today, well, that's the rest of today, into tomorrow and even into Friday, because we probably can't cover everything all at once. This is the equivalent of the equilibrium condition, right? That equality is true when we are at equilibrium. That is where we got to when we started off with saying any change for a real system in its Gibbs free energy always ends up going down. The equivalent statement for that is this expression that we've got right here. That was what I had written at the beginning of the lecture, so we're going to figure out this one tomorrow. And we're going to focus on this one, the right-hand side, today. The right-hand side is also the one that we, well, actually, I'll get to it in a minute. This one, I had already defined that as K. By the time we are done, we're going to have about a dozen different Ks floating around. Some of them are uppercase, some of them are lowercase. Everything that we're going to be dealing with here is uppercase K, a big K. That's hard for me to draw here. It's kind of hard for you to tell whether that's an uppercase K or a lowercase K. Everywhere today, tomorrow, and the next day that you see a K, it's always uppercase K. When you see us start writing this later in the quarter, when we introduce the lowercase Ks, I put these little caps on there, just so that you're reminded that's an uppercase K and not a lowercase K. But just to save time here, because we only have one K right now, we're going to talk about that particular K everywhere. That's the equilibrium constant. We have seen that probably somewhere in chemistry. It is defined in that particular way over here on the right. Interestingly, it's called an equilibrium constant, but it's a function of temperature. Again, not my call. I didn't do that. It is a function of temperature, but they call it an equilibrium constant. At any rate, everything on the right that we're dealing with here is a function of nothing except temperature. All we need to know is the temperature of the reactor, or for that matter, the temperature of the reaction, because the reactor can vary in temperature from one side to the other. All we know is the temperature at a slice of that reactor. And that's what we're going to try to figure out today. The stuff on the left is a slightly more problematic one. That's a function of temperature, pressure, and the moles of I. You could replace that moles of I with squiggle if you want. They're sort of like interchangeable. All that other stuff goes over there on the left. But the stuff on the right, maybe that's kind of why they went with a constant. It's only a function of temperature. If all we know is temperature, we can figure out that whole exponential term on the right, and that is what this K is. Tomorrow we'll figure out the G function of temperature, pressure, moles, and squiggle. Today we'll focus on temperature. How do we get temperature? Or sorry, how do we get closed form for that? We're going to work on this G parameter up here, because we have a couple of ways to make that more useful. The way that we make that more useful is to use the definition of G. So if we say any species I in its reference state, that was simply defined as HI, so enthalpy, minus T times the entropy. That was that same kind of definition that's not, there's no theory behind that, right? We just find that's a much more useful quantity to carry around. Same way enthalpy was defined as internal energy plus PV. Those terms just come up a lot, so we use them a lot. There's no math, there's no thermo behind that. It's just a useful thing. What we can do to that is if we take this expression, we're going to multiply the whole thing by nu sub I, and then we're going to sum over all those components. Right, so we're going to do the little summing thing right here. After we do something like that, we get a bunch of these deltas again. So we get a delta G circle is equal to delta H circle. I'm going to move down. I'll keep writing. You can see that if I write over that logo, right? Yeah, that doesn't show up too bad. Minus T delta S circle. So that's why I brought up that delta a lot. We're going to see a lot of those deltas. I didn't show every step of that right there because it would be a lot of lines, but we're going to do that several different times. The other two variations that we had from 100 was that any change in enthalpy, it doesn't have to be enthalpy with a circle, but everything we want is with a circle, was equal to the heat capacity times the change in temperature. There was another term here. If you remember back to the rigorous definition that we had in thermo, there is another term that's there, but that term was multiplied by a change in pressure. And remember, the standard state is always at 1 bar. It never changes from 1 bar. So there is actually another term there in the rigorous expression for DHI, but that term goes away because the pressure change is 0. Because we're always talking about the standard state. So that is a rigorous definition. We haven't made any approximations there. That's real as long as you're operating at constant pressure. If we do the same thing again, so we're going to take this, multiply it by nu sub I. After we multiply it by nu sub I, we're going to integrate each one of those from a reference condition up to the circle condition. And then we're going to sum it all up. Lucky for you, I already did that, so we don't have to do anything like that. The end result, then, is that a delta H circle is equal to some reference delta H circle plus an integral of temperature. Integrating anywhere from any T ref up to any temperature that we want, times a delta Cp times a dt. Delta Cp, remember, what was the form that we used for Cp? Whenever you had to calculate a Cp in 100, what did it look like? A, B, C, D, right? It wasn't the world's most user-friendly kind of expression. It was usually Cp as a function of T was something like A plus Bt plus Ct squared plus dt cubed. That's what's inside. This integral is no joyride. Don't sit down and just for fun try and evaluate that integral. There's nothing wrong with that integral, right? We know how to integrate a polynomial. It's not that hard to integrate it, but there's one of these terms, Cp of t, for every single species that's in your system. which means if I have 4 species and all 4 of those species have an A, a B, a C, and a D, that's 16 units of A, B, C, and D that I need to carry around. We rarely evaluate that thing by hand. We have a spreadsheet for that, which is what we will get to momentarily. Nevertheless, we need that particular term. And we need one other term, which was to handle that entropy. DSI circle was defined as Cp times the change in temperature divided by the temperature. If we do exactly that same procedure, we're not going to write all of that out, we get something that looks really, really similar. Delta S ref circle plus integral from T ref to T of delta Cp times dt over T. So what we're going to do is take these two expressions. Oh, that was supposed to be leads to, not equals. Take these two expressions, this one here, and this one down here, and we're going to substitute them into this particular expression. By the way, sometimes it depends on what book you're reading or which derivation you're following. This is not always ref. Sometimes they will write this as delta H 0 with a circle. A, zeros and circles look really similar, so I don't use them. B, we have another use of zeros later to talk about initial conditions or entry conditions. And then it becomes, you can have a single expression where subscript 0 has 2 different meanings, and it's kind of hard to keep track of it. So I tend to use the word ref. But you will also see it written as delta H 0, which is okay. Not a problem. All we have to do after that is a little bit of algebra. And I say like little bit as in, sit down and give yourself 3 hours to rearrange something like that. But there's no other step beyond that other than more algebra. Once you do all of that algebra, you end up with the equation that we want. Again, all of that algebra is taking this expression with the star, that expression with the star, putting it inside that one, and then taking the result of that and putting it inside here. So it's just a series of substitutions in there. It's not that bad, but it's long enough that we don't really care. As a result, what we see is this. The exponential of minus delta G, we've switched the signs there for good reason. Or actually, I think I forgot a sign anywhere. Before we leave, somebody yell out sign change, and then I'll go check my sign somewhere else. As a result, what we have is this. Exponential minus delta G ref with a circle over RT ref. We have that term times another term. This is times, not summing. Times the exponential of delta H ref, circle, divided by RT ref. Wait, it gets better. Nobody believes me. Everybody's silent. T ref over T times one more times another exponential of the following, which is minus delta H. I call this CORR. We will define that in a minute. It's a correction term plus delta S correction over RT, or sorry, just over R. We're going to annotate the crap out of this, which is why I didn't say anything on there. There's 3 exponential terms here. We deliberately pulled them apart in that particular way. You don't have to pull them apart. You can put them all back inside a single exponential and everything will work just fine. The reason that we pulled them out is because they have some meaning associated with them now. We usually define this very first exponential as k sub 0, right? First thing, well, I don't know. If you're into computers, yeah, the first thing usually starts at 0. That's our first estimate. What K0 does is gets us started. It's usually a pretty awful start. The reason that this gets us started is because delta G ref is equal to the sum of the stoichiometric coefficients times delta G of formation. The advantage here is this is tabulated. You can go look up Gibbs free energies of formation, just like we would have seen enthalpies of formation in CENG 100. They probably popped up somewhere along the way in 102. But at any rate, it gets us started, right? We can just go look up a bunch of Gibbs energies of formation and use those to calculate what that delta G ref is. Remember, whenever you see that delta G, that's talking about summing over the stoichiometric coefficients times the thing. How come we went from G ref circle to GFI? We just need any old G that we happen to have laying around. The only one that we ever have laying around in a table somewhere is the one for formation. And so that's the one that we use. It gives us a number. That gives us somewhere to start. The next one that's on here, this one, that exponential term is usually defined as K1. And what K1 does is adjust K0 for some temperature. Right? The problem with K0, when we wrote K0, the reason why it's not particularly helpful is, well, it is actually very helpful. It's just a starting point. Whenever we look up those Gibbs energy of formation, they're always at like 298K, 298.15K, something like that. Very rarely do we ever have a reactor that runs at 298.15K. But that's the temperature that goes into the expression for K0. We have to adjust that because reactors don't run at Tref. And the way that we do that is through the K1 parameter here. K1's got another one of those delta H terms in it, the delta H ref. Delta H ref looks just like, oh, wrong color. The delta H ref that we've got right there looks like the sum of the stoichiometric coefficients times the enthalpy of formation of I. Again, we just need any old enthalpy that we happen to have laying around. Again, the only ones that we have laying around are the ones that we can look up as enthalpies of formation. So now I've got something that's tabulated. I can get a K0 from tabulated values of Gibbs free energy of formation. I can adjust K0 for temperature by looking up delta H of formation. The last step that I have to do is by the time I get to that particular step, the delta H ref, I have assumed that that is constant. And it's usually not constant. It's usually a function of temperature. And that's what this last one does. This last one is a correction that we call K2. And what that one does is adjust delta H for temperature. That adjustment is usually small. There is no way in the world you can ever neglect the adjustment for K1. You always have to do the adjustment for K1. Pretty often, though, K2 is kind of small. It can be on the order of like maybe a 0.9, something like that, versus 1. And so that one can sometimes be ignored. The correction terms that we've got in here are those integrals that we saw floating around a minute ago. Those integrals were, where did I write them? Oh yeah, they're there. These delta T ref to T delta Cp dt. And another one for the entropy. But again, we don't evaluate those things by hand. We always use something else to express them. So the end result that we have is this expression, which is that the equilibrium constant K has to be equal to K0 times K1 times K2. There's a name for that, which is the Van Hoff equation. So if you ever hear me say, use the full Van Hoff equation or use the Van Hoff equation, I'm talking about you need to calculate K0, K1, and K2. There's also a version of the Van Hoff equation that's a little bit simpler. You can define a shortcut version, which is just K0, K1. The shortcut version of k is just k naught k1. That one you can actually calculate by hand. That's not too bad. You're going to practice that on the first homework problem that you've got. In fact, the first homework problem is doing exactly those two steps up at the top to calculate k0 and k1. That one's not awful. Nobody ever does the full Van't Hoff equation by using k. That's what we have the spreadsheet called kcalc for, which is on our TritonEd site. We are down to about a minute now, so we're not going to go over that particular spreadsheet today. We'll hit it tomorrow. But this is the shortcut Van't Hoff equation, and that's the full Van't Hoff equation. If you're working on your homeworks, you can still get problem 1 with just the shortcut version, because I just gave you tables of GF and HF, so you can calculate that one okay. You can try to work on the kcalc spreadsheet if you want. It's fairly straightforward, but we are going to go over an example of that tomorrow. And then you can also solve the very last problem. Problem 1.4 is an alternate way of doing all of this that you don't need any of this for, so you can work on problem 1.4 as well. And then we'll cover enough tomorrow to take care of the other two, and that homework's due on Wednesday. So I will see everybody tomorrow at 5 o'clock.